And so a cycle, we define that as the result of multiple processes working together. We're jumping from one energy state to another to another. Now, the processes are each of those directional lines or paths that we have on a cycle. So each one changes from one energy state to another, and that shows that the conditions have changed. And these describe how we put work in, how we take work out, how we put heat in, and in the case of a closed system, how we take heat out. Technically, with an open system, you kind of let the heat out. So we describe these processes in terms of what holds constant. So an isobaric process is at one single pressure. There is no change in pressure throughout the process. The volume and temperature can change. Isometric processes, or isochoric, depending on who your teacher is and who you're talking to, you go ahead and remember both, sorry if that's confusing, is one size or one volume that you're working with. So the change in volume is zero, and the pressure and temperature change correspondingly. An isothermal process, or isotherm, is at a single temperature, so the pressure and volume will gradually change. Now, adiabatic looks like it kind of breaks the naming convention because we go with iso this, iso that. Adiabatic is from an old Greek word that means impassible. All three variables, pressure, volume, and temperature, can change, and there's a gamma function we can get into later that connects to all that, but that's more advanced than we need to know currently. But what matters is that the change in the heat is zero. Heat does not leak in, and heat does not leak out. And there's a special type of adiabatic process called an isentropic process, one entropy state. So the change in entropy is zero, and entropy is useless heat. Once you have a massive buildup of entropy, it's done. It's garbage, it's junk, and you throw it out, right? And the idea with thermodynamics, one of the laws of thermodynamics, is that the entropy of the universe will always increase. It will become more disordered, and there will be more and more useless heat. Other books and other sources tend to call entropy S, usually capital S, but in this class it appears that we use delta H. I don't know why, don't ask. I honestly need to go read the book and figure it out and check the slides from the class, but overall, same concept. So this is what we typically refer to when talking about a cycle. This is one example, and when I get to ideal gas law, I'll explain how P times V, or P dV, is related to energy. Actually, I can just do that right now. The integral of pressure times the change in volume is work energy. That's one formula for it, but you'll find that through some unit conversion, you'll find that both sides of the equation, PV equals nRT, that's the ideal gas law, is energy equals energy. They're both in units of energy. We find that other formulas and other dimensions that are used to evaluate cycles also result in energy. And this is where it starts getting really interesting in terms of what we have here to work with. More importantly, we take a look at this, we see we have energy states, right? Energy states punctuate a cycle. Now, this is the way I want you to think of it. The energy state, and we use a driving analogy. The energy state is your starting point and your ending point. What matters is that you got there, but the path you take impacts your efficiency. That's which road you took to get there, which path you took to get there, and that can impact your efficiency. Now, normally, it's not too crazy where you have lines like that first one I erased that goes up and swoops in like that. Normally, they comply more with isothermal lines. They stay kind of close to that. Typically, and if you remember from Calc 3, there's these things called contours. Let's say this is an example of a process or a line or contour, more specifically, where everything is at the same temperature. This would make this line an adiabatic line because we have added heat. The temperature has gone up. As you see, this line is steeper. It's passing from one contour to another, right? Now, the route that you take around a cycle is also important because it tells you which way energy is being moved. So if we run it as a heat engine, it means it goes up this way, out to the right here, then down, and it exhausts its useless energy in this process. When the cycle looks like this, the engine is extracting work. Think of it like the engine in your car or a jet engine on a plane. When it goes the other way, however, you're putting work into a device in your system that is grabbing energy from the environment and moving it somewhere else. You are reversing the process. And the reason we can do this, the reason we can explain it like this, is again, here, integrating PDV, but it is a path-dependent interval. Now, most cycles in real life, they're a little bit blunted, and that represents a loss in efficiency because the area enclosed in the graph of the cycle, it's not enough, hang on. Because the path enclosed in the cycle, the area enclosed in the cycle as we integrate is the energy that we can use. That's important to consider. Now, our efficiency can be derived from this. It's the area that we use over the full potential enclosed area. Or perhaps I should change the arrows around. Let me go do that so it's less confusing. There we go, slight correction done. So this, again, we're back to the way where it looked like an actual engine doing work. So an open cycle has a really interesting characteristics, but it's usually not reversible, and the change in energy states of the system is not equal to zero. That's because the system mass is entering with one energy state, going through a set of processes to do some kind of work, and it's coming out with a different amount of energy. We put a dotted line here because later on when we get to calculating energy from a cycle, when we use equations for the different processes, we'll figure out that we can sort of use an imaginary process to figure out how to close off the system and get the usable energy out of the total energy that the heat engine dealt with. But ultimately, that's why the change in energy of the system is not equal to zero. Remember, the system is defined by the mass that participates in a cycle or in a set of processes, given the changes in conditions we use. But what we have with a closed cycle is that the mass is kept in the system. So in order for the cycle to complete, you have to bring the mass down to the same energy state it started with. And so we can say in the end that the total change in system energy brings us right back to zero. We return to the start. With an open cycle, it's in one end and out the other. So this is how a typical cycle works, especially in a heat engine, right? You have your compression phase, which is getting the fluid into the right condition to accept energy and get a reaction to start. Usually you would compress for something like combustion. So your volume decreases, your pressure increases, and we'll assume this is adiabatic, where you're adding work energy and keeping your heat energy. So yeah, that's your compression. And then you have your heating, and that gives you what you need up at the top. Then you extract work through this side over here. Well, notice we have a ton of energy going out to here, so we get to use up a decent chunk of it. But at the end, there's a certain amount of energy that is just not worth capturing. So you end up with heat that you're unable to use, and that's a massive source of inefficiency. So you have to get rid of that and cool your system down.